point 2 of your notes, we're looking to see if f of x is a linear function or an exponential function, and we're going to do that by taking a look at whether the ratio is constant or whether the difference is constant between two consecutive terms here. So at x equals, we can start with x equals -1, our output is 2.8, and at x equals -2, our output is 1.12. So I can look at the difference in those numbers, difference being subtraction, and take 2.8 minus the 1.12 and see what I come up with. I have 1.68, which means if I now take at 0 the output of 7 and subtract 2.8, I should get roughly 1.68. And if I do, then it's likely to be a linear function. If it's not 1.68, then it's not a linear function. And I get something not close to 1.68. So I think, well, maybe it's a fluke. Well, if I try 17.5 minus 7, that's not going to be close either. You can see what that difference is in those two consecutive terms. It's 10.5. So our numbers are not the same here, but what I can do is look at now the ratio. If the ratio is the same, then I can conclude that they're exponential. It's an exponential function. So if I take 2.8 and divide it by the previous term, 1.12, oops, back up there, and see what I get, 2.5, and then do the same for 7 divided by 2.8. And that's 2.5. Well, that's looking much better. All right, I can try 17.5 and divide it by 7. All right, so it looks like we have a winner. And you can then finish up by taking 43.75 and dividing by 17.5 as well to confirm that you do get a number either 2.5 or really, really close to 2.5. Then we can say that that function is an exponential function, or it models that behavior anyway. So call this one exponential. We came up with a ratio of 2.5. So if I want to write the equation for f of x, I already know what my growth factor was. I don't know what happened to my page here. My growth factor was 2.5, or that ratio was 2.5. That's my a value. And then I just need my initial amount. So I look at where x equals 0, my y-intercept for f of x is 7. So my function is going to be f of x equals my initial amount, c, times a, 2.5, to the x. Remember, you can't do the 7 times 2.5 because the 2.5 is being raised to the power. So you have to do powers before multiplication. With that same idea, we can look at whether g of x is a linear function. And this one might be a little easier to see. It looks like it bumps up by 0.2 each time. Or if I subtract, the difference will be 0.2 in between each of those. So if it's the difference between terms is constant, we're going to look at g of x being a linear function. And the average rate of change, or my slope, is 0.2. That's how it changes for one increment in x. It changes by 0.2 of an increment in the y value. So now write the equation for g of x. So we're going to write the equation of a line. G of x equals the slope, 0.2x, plus b, the initial amount. Well, I go back to x equals 0 is my initial y-intercept for g, which is 0.5. For my next problem, we're going to kind of do the same thing. We're going to be given 2 points, and we want to write a linear equation, and then we want to write an exponential equation using those 2 points. So if I'm going to write a linear equation, I need to know the average rate of change, or the slope. So calling my first point x1, y1, my second one x2, y2, I'm going to start with 22,000 minus the y sub 1 value divided by x sub 2 minus x sub 1. So that's going to be 7,000 on top divided by 5 on the bottom. So I'm going to have 1,400, and that's town's population per year. The y-intercept is given to me in this point, because when x equals 0, there's my y-intercept, 15,000. So when I go to write the equation, y equals mx plus b, I know what my m is, and I know what my b value is, 15,000. And that would be your equation, your linear equation, representing those 2 points, or going through those 2 points. Now we're going to write an exponential equation that goes through those 2 points. And again, we need the c value and the a value when we write an exponential equation. So to figure out your c value, that's your initial population in this case, that would be 15,000. And then it's a to the x. Then we need to find a. So to find a, I'm going to plug in the second x and y value in here into my equation and then solve for x. So my second point is 22,000 equals 15,000 a to the x, which is 5, or the 5th power. To solve for a, I need to get rid of the 15,000. So I'm going to divide both sides by 15,000 because it was hooked by multiplication to that a. So I have a to the 5th equals, and then do the division here. And when you do that, it comes up 1.4 and then a whole bunch of 6s repeating. So I'm just going to put a bar over that. But that's a to the 5th. I just want a. So to remove the power of 5, you do a root of 5. So I'm going to take the 5th root to both sides of the equation. Now here's where your calculator can kind of help you out a little bit. All right, notice back when I asked you to take the 22,000 and divide it by 15,000. Okay, so there's my big long decimal. Leave that on there, but now I want to figure out what's the 5th root of that. So if I go into my math menu, okay, I can see right here on my calculator, if I go down to the number 5, it's waiting for me to put the root in. So see where it said answer? I don't want the answer there. I want the number 5. And then it knows that's the x that I want it to be. And then I can scroll over and then do second and put my answer from above, the 1.46666, under that. And then hit enter. So that's the 5th root. That 5 in front is the 5th root of the 1.466. You're going to have to play with your calculator to see how it handles it, but it should come up about 1.0796. This says to round a to 3 decimal places. So 1, 2, 3, that means I look at the 6 and round the 9 up, which means that now becomes 1.080 for my a value. Then I can go back to my function, or my equation here, and plug in the a. So it's y equals 15,000 times 1.080 to the x. And that's the exponential equation.